So far, you've seen how to solve the single source shortest path problem. This is how to find a shortest path from a single starting vertex to all other vertices. So we obtained, using some of the algorithms you saw earlier, a shortest path tree, which gave a shortest path from that single starting vertex, which was the root of that tree, to everything else. And there were a few approaches, depending on what kind of graph we had. And this was, initially you saw how to do this on an unweighted graph. So this is that the edges didn't have a weight associated with them. In effect, this is just that every edge contributes the same weight. Then you can use breadth first search. So in this sense, we're just minimizing the total number of edges to get from point A to point B. And we could do this in linear time. If we have a weighted graph, then still we have a few options. If that graph is directed and it's acyclic, then no matter what kind of edge weights there are, we can still do this in linear time using a topological order and relaxing edges for every vertex along that order. If there are non-negative edge weights, but we don't have a directed acyclic graph, then you can apply Dijkstra's algorithm, which runs in big O of m log n time. If there are negative edge weights, then we can't apply Dijkstra's algorithm, but instead we can apply Bellman-Ford's algorithm, which runs in big O of n times m. Now this is usually the case when creating an algorithm. We have, in a very specific case, a very efficient runtime, but this is restrictive in the sense that it only works on unweighted graphs or on graphs that are directed and acyclic. And as we increase to the more general situation where this would handle then anything, non-negative or negative edge weights, this would handle anything on any kind of graph, then we have a more expensive runtime. Now another variation of a shortest path problem is to find a shortest path from all vertices to all other vertices. This is known as the all pairs shortest path problem. And it's quite common, as there's a lot of problems that can be reduced to solving this one. To give just one example, facility location problems. Say you want to find a vertex which minimizes the maximum distance to all other vertices. This would be a good place to put a new hospital because it's close to everyone else. So if distances between all pairs are known, then we could simply pick out that one whose maximum distance is the smallest. Now in order to solve this, we definitely need at least n squared time because we have that many pairs of vertices to consider. But how could we solve this? Because we know how to find a shortest path from one starting point to everyone else. So we could apply any of the algorithms we talked about before n times, depending on what kind of graph we have. If we know it's unweighted, then applying the breadth first search algorithm n times gives us an n times m algorithm. Same if we were to apply if the input graph was a directed acyclic graph, we could call this n times once for each of the n vertices, since we want to find a shortest path from each vertex to everyone else. Gives us a total big O n times m algorithm. Or if we knew that all edge weights were non-negative, we could call Dijkstra's n times and we would get an n m log n algorithm. These are ways in which we can solve the shortest all pairs shortest path. Or if we have no such restrictions, we have negative edge weights as well, then we could call Bellman-Ford's algorithm n times, once for each starting vertex, which gives us an n squared m algorithm. Now remember at this point that m, the number of edges, m, can be as large as n squared. So if we were to put, let's say, this one in terms of n, this would be big O of n to the power of 4. Now, like I mentioned before, we know that this will require at least n squared time because we have that many pairs of vertices to process. And I'm going to show you in the next slide that we can solve this even better than what the previous algorithms would give us, just in a general case for any type of graph, no matter if it has negative or non-negative edge weights. We can do this in n cubed time using a variation of Floyd-Warshall's dynamic programming algorithm. But even right now, we don't have a better running time than big O of n to the third power. There have been some improvements to this over the last, so many decades, but we still don't have anything in truly subcubic time. And there's a conjecture right now that there is no such algorithm, that it might not be possible to do better than n cubed. So let's see how Floyd-Warshall's algorithm could be adapted to solve all pairs' shortest path. Now remember that Floyd-Warshall's algorithm, let me just recall for a second. Floyd-Warshall's algorithm you originally saw in order to solve the transitive closure. So the transitive closure of a directed graph was a graph which had all the same vertices and edges, and it would additionally have an edge from one vertex to another vertex, say from vertex A to vertex B. We would add this edge in the transitive closure if in the original graph there was some path which connected vertex A to vertex B. And Floyd-Warshall's algorithm accomplished this by gradually building up this transitive closure. And it would separate all vertices in the graph. It would label all of them from 1 all the way up until, let's say, n. And at any given point in time, it would consider the first so many vertices. And for every pair of vertices, check to see, is there a path which connects vertex I to vertex K? And if there's a path that connects vertex K to vertex J, where along this path, we could have as intermediate vertices, so not the endpoints of this path, but as intermediate vertices, we could choose from the first k-1 vertices. So maybe some of those vertices participate in that path, or all of them, or only a portion of them. If there's a path connecting I to K and K to J, along which the intermediate vertices of that path consist of only vertices from the first k-1, the set of the first k-1 vertices, then that means there's a path from I to J, in fact, this path exactly, which connects I to J and uses only the first K vertices, now that we're introducing this new vertex K. So we're going to use the same idea here, but rather than just checking for the existence of a path, we're going to keep track of which path we do find and which one is shortest, which one gives the minimum distance for any pair of vertices. So rather than building up a graph, we're going to build a set of distances between all possible pairs. So this is from distance from some start vertex to an end vertex. So we can label every vertex from 1 to n. That way we can uniquely access this just as a two-dimensional matrix in constant time of the distance from some starting vertex I to some ending vertex j. And we know some of these distances already. So if we have the same start and end vertex, the cost associated with going from one vertex to the same vertex is 0 because we're already at that vertex. For every edge, each of the m edges we have, we can set the distance from that vertex I to vertex j to be the weight of this edge. We may find an even faster, more efficient way of getting from I to j later, but we can initialize what we know already based on the weights of the edges we were provided. And then for every other vertex pair, we set its distance label to be infinity. So because we want to find a distance between all pairs of vertices, the distance label here is based on a vertex pair from a start and an end vertex. Okay, keeping consistent with Floyd-Warshall's algorithm, we'll now iterate over all possible intermediate vertices k, and we want to find the distance label for all starting vertices I to all destination vertices j. And we can set this distance label as the better of two possible outcomes. Either we already had a short path to get from vertex I to vertex j, which used only the first k-1 vertices as intermediate vertices. Or we find now that using vertex k, we can find an even better distance from I to j, a better path, a shorter path. And that would be a path which goes first from I to k, which uses as intermediate vertices only the first k-1 vertices, and then from k to j, which uses the first k-1 vertices as intermediate vertices. So the length of this path from I to k we have computed already, plus the length of the path from k to j gives us the distance from I to j using that path. So the length of that path which uses k. So we take whichever path would give us a shorter length. So the total running time of this just is the same as Floyd-Warshall's, his big O of n cubed. And again, we don't have a way to do any better than truly subcubic time at this point. It may be possible, but this is an open conjecture. So there are still some interesting problems to be solved in algorithms right now.